I'll be discussing in brief about the planetary atmosphere and how to theoretically one can model the planetary atmosphere. So if you can see, this is a schematic which gives the various processes that make up the planetary atmosphere, and it contains different aspects which I will discuss in detail in the subsequent. So planetary atmosphere has several processes, so which makes up the planetary atmosphere as a whole. So all these processes can be classified into three categories as shown here. So the first can be a radiative processes, which is basically the interaction of solar radiation with the atmospheric species. Then you have chemical, which is the atmospheric chemistry. Then there are dynamical and physical processes. So all these three categories of processes are coupled to each other. And then if one has to understand or simulate a planetary atmosphere, so all these three processes have to be taken collectively and simulated together. So to give a complete picture of what is happening in the atmosphere. So if we look at the structure of the atmosphere, so basically we talk about the physical structure. It is dominant by three basic parameters, which is the pressure, density, and temperature. So if we look at the physical structure of the atmosphere, so generally what we call as the physical structure of the atmosphere is maintained by an hydrostatic equilibrium. That means it is basically, you can see this P equals to NKT. So it is governed by three basic parameters. One is the pressure, another is the temperature, and the one is the number density. Number density is the density of the molecule or species, whatever is available in the atmosphere. Whereas the pressure is directly related to temperature, but also it has a relevance with respect to the pressure or the number of molecules which are present in the given volume. So when the atmosphere is in equilibrium, so what happens is that a planetary body has a gravity. So this gravity tries to bound this atmospheric density or these molecules to the surface. Whereas whatever is the lighter species, they start escaping. So in turn, what happens is that at equilibrium condition, the pressure gradient, whatever is the delta P, the variation in the pressure, gets balanced by the gravity. So which can be written like this: the pressure is, we know that it is nothing but net force per area, and the force is nothing but which is produced by the differences in the pressure as a function of height or altitude. So it can be written like this, where you have at a given height, you have a pressure P, and at a other height, maybe lower or upper, so you can have a delta H and DH height, you can have pressure P, H plus DH into area. So you can have the delta P into area. Then if you look at the counter gravitational force, it is like minus m is the mass and g is the gravity. So you will get, so for pressure, you can actually write in terms of minus rho, density, gravity, A and delta H. So you have delta P into delta A equals to minus rho, which is the density G, A delta H. So if you put it in a common form, like the rate of change as a function of pressure as a function of height, delta P by delta H is nothing but a negative product of density as well as the gravity. So this is what at equilibrium condition is defined as, and this equation basically governs how the atmosphere held by the gravity of a planetary body, and this equation is called the hydrostatic equation. This is the fundamental and the first basic what is a mathematical formulation or equation that governs the physical structure of an atmosphere. So if we have this hydrostatic equation, so there are two parameters, one is the pressure, another is the height. So how does it change? How does the pressure changes with altitude? So what we can take this hydrostatic equation and then we can integrate it. So assuming the temperature is constant, then we get an equation like this: P equals to P naught exponent of minus Z by H. So if we look at density versus altitude, you get this kind of measurement because they are interrelated, pressure and density. So you get rho equals to rho naught exponent to the power of minus Z by H. where h is a parameter called as scale height, which is written as kt by mg, which is sometimes also written as RT by MRG. So where scale height is defined as the height at which the species or the number density in this case decreases to 1 by E of this previous value. So if you have a surface, the scale height is where the density decreases by 1 by E of A, the surface value is termed as the scale height. So if we apply these parameters and derive what is the scale height for various planetary bodies, we get this table. If you look at Venus, Venus has a dominant gas as CO2, which is mass is 44. Then its gravity is 8.8 meters per second square. At temperature is around 750 Kelvin. Under these conditions, if we put it into the hydrostatic equation, then we get scale height is 16. Then whereas if we have Earth, where is the dominant gases nitrogen and oxygen, and whose mass is 29, and then you can have 9.81. So temperature is taken as around 290 as so your scale height is 8 kilometers. Whereas on Mars, if you put the same thing, you get 12 kilometers. What does it mean? It means that how the number density, what we see at pressure, what we see at the surface changes, how fast it changes as a function of altitude. So this is the fundamental information of the structure of a planetary atmosphere as we go from the surface towards the upward side. So now, so once we have a surface, what is a species as a function of altitude, so what happens? So this is the basic fundamental physics. Then what happens is that there is sun, and the planet's atmosphere is continuously subjected to solar radiation. So this solar radiation will continuously, affects the sun surface, reaches the sun surface. But if it is an airless planetary body, so there is a possibility that the entire solar radiation reaches the surface. But if there is an atmosphere, it is possible that the atmospheric species have a capability to absorb a part of solar radiation, because the solar radiation is complete, has a complete electromagnetic spectrum, and depending upon the selective absorption of each of these species, they may get absorbed. Let us consider that if there is no atmosphere, just there is a surface. Basically, the surface temperature is determined by an equation called as energy balance equation, which is nothing but, so an ideal black body, it absorbs the radiation and then it emits the radiation in long waves, that is infrared. So basically the energy balancing is nothing but, so power absorbed from sun or solar radiation, then power emitted in thermal radiation. So usually the power emitted in thermal radiation is manifested in terms of the surface temperature. So using this energy balance, we can actually calculate the surface temperatures at temperatures of any medium which is incident by a solar radiation. So we use basically for this energy balance, we use this equation. And this equation on the left side, you can see that you have a solar constant, which is S naught. S naught is nothing but the solar insolation, which is around 1400 watts per meter square at the top of the atmosphere. Cos theta is actually the angle at which the solar radiation is received. It is nothing but you can term like in terms of latitude. If theta is 0, then equator receives the complete overhead sun. So like if you say 45 degrees, so that much of angle. So theta, you can use the latitude or an angle. Then 1 minus A is the albedo, and R is the sun-planet distance, which is the distance between the source as well as the planet. Then on the right side, you have sigma, which is given Boltzmann constant. Then T to the power of 4. Then you have 4 pi R planet square, which is nothing but considering the complete spherical surface. So if we put this, most of them are constants. So if you put that, then the whatever sun's radiation that is that falls on Earth or any planetary surface, the temperature is defined as the fourth root of the sun's radiation that falls on the surface. And the solar constant at Earth can vary around 1360 watt per meter square, with a few tens of watts per meter square as a function of season. So if there would not have been any atmosphere or any gases present, the solar radiation would reach the surface and it will heat the surface based on this, and we would see a surface temperature which will correspond, if there is no atmosphere, then it will correspond to around some 400 Kelvin kind of thing. But on Earth, it is not the actual temperature. Why is it so? It is because Earth has an atmosphere, and the atmosphere has a capability to absorb a part of solar radiation. So I'll come to those details in next. So if we look at the basic hydrostatic equation and the interaction of planetary atmosphere with solar radiation, because planetary atmosphere is not uniform, it is basically a heterogeneous in nature, which different compositions or species at different altitudes and also different pressure distribution. So the solar radiation also interacts differently in each of these regions. So if based on that, we will have a physical structure of temperature based on the solar radiation, how it is absorbed. And if we can see that this solid black line gives the thermal structure of vertical thermal structure of the Earth. So where you have somewhere around 300 Kelvin, which gets reduced to almost near 200, 220 Kelvin at around 10 kilometers altitude, then it starts increasing. So you have a temperature decrease as you go with altitude, wherein it starts increasing. Then again you have a second again a decrease, and again start increasing, and you have another temperature decrease. Basically, it occurs at a in the mesosphere. So, so this kind of structure, thermal structure, based on how the temperature changes, so we can actually divide it into various layers. Unlike the Earth, if you look at Venus, it has completely a different thermal structure. We do not have this kind of reversal here. So where temperature decreases up to an altitude of 8 kilometers and more or less it remains constant. While in the case of Mars, you have a thermal structure completely different from what we have at Earth and Venus. So you have temperature not decreasing as drastically as Earth or Mars, but it still decreases and up to 40, 50 kilometers, and then it is more or less remains constant. So based on this, what is the basic reason for this? This is because the basic reason for this kind of structure for different planets is the radiative processes which are involved in this, because all these do not have the same composition. The composition of Earth is different from Mars, it is different from Venus. So depending on this composition, how the solar radiation interacts with this, the atmospheric species, so this thermal structure changes. So we look into it a little more detail in the next slide. So what are the radiative processes which create this? So why these radiative processes are important? So if we want to actually model or mathematically define and derive the processes which are prevailing in the planetary atmosphere, so we have to know how the solar radiation is absorbed at different heights depending on the species what are produced. So they can be different mechanisms. So these are the four main mechanisms which can happen. So one is the ionization. So what happens in ionization? So whenever a solar radiation or a photon interacts with a molecule, so it with an atom, so it will detach an electron. So it will ionize the species and produces a separate lone electron. So this process of removal, so it creates ions and electrons. So what it creates a plasma, and this plasma is what it does is that it is because of the interaction of solar radiation with the neutrals which are present there, which creates electrons and ions, which is the plasma, which usually happens at a relatively high altitudes. And next is photo dissociation. So when you have a photon, so it has the capability of dissociating the molecular species. Like it can destruct a molecule and produce two new species. This is photo dissociation. In some cases, it will neither ionize nor dissociate, but it can scatter. What it will do is it will just change the direction of the photon. So scattering may happen. Or in another case, what can happen is the complete photon's energy can be absorbed, which can create to some kind of heating. So we will look at some details about these kind of processes in the next subsequent slide. So before going to that, just a brief. So once you have a what do you say, atmospheric pressure difference, which is based on the number density, then you have solar radiation, which interacts with the surface. So then it gives rise to a atmospheric thermal structure as seen here. And basically, this structure is a resultant of a process in the way the solar radiation interacts with the atmospheric species. So if we take the case of Earth, an example of Earth based on the temperature, you can see at the surface up to the troposphere, where we have a temperature inversion. So this is basically what you have is greenhouse gases, you have a trapped infrared, you have radiation from the surface, you have convection, which is more important because you have high density, means you have winds, etc. So similarly, as you go to the stratosphere, your density decreases. You have very less, almost you do not have any convection, and mostly this part of the atmosphere is heated by UV light, ultraviolet. So ultraviolet is transparent to the top layer, but ultraviolet gets absorbed here. So similarly, if you go up, so what we call it the thermosphere and ionosphere. So here you will have X-rays. So this X-rays heat and ionize the gases in this region, and beyond which you have an exosphere, which is heated by solar ultraviolet, X-rays, and most of this here, the density is very small, and this is a region where whenever you any species and a atom or a molecule gets a little bit of what is that ions, whatever is there, will get little bit of energy from the radiation. They tend to escape the planet's gravity, and they tend to escape the space. And if you look at the other way, so this is with respect to the thermal structure. Whereas if you look at what is the windows, which the solar radiation comprises of the entire electromagnetic radiation, right from your X-rays to visible, which is shown here, even it has a broad range. So the X-rays can penetrate only up to this region, where UV can penetrate, come up to the stratosphere, whereas visible can come here. Whereas a part of infrared also reaches the ground, and whatever heating that happens at the ground is also reflected back as an infrared region. So this is how the solar radiation interacts with the atmospheric species, as an example for Earth, which creates this kind of thermal structure of the Earth atmosphere. So then we have seen the decrease in temperature. So this is a phenomenon what is observed. If you do an observation, then how do we derive it? So the temperature decrease in troposphere can be derived based on simple first law of thermodynamics, which tells about the energy conversion, which conservation, which is nothing but energy equals to internal energy plus work done, which can be written by this equation. So the rate at which the temperature falls with altitude is given as a lapse rate. So if we use this equation and take three examples as we have done before for Venus, Earth, and Mars, so you will have the lapse rate has like this. So Venus, the lapse rate is around 11 degree per kilometer. Earth, it is 10 degree per kilometer, whereas for Mars, it is 4.5 degree per kilometer. So which results into the temperature decrease as a function of altitude. Okay. Now we have seen that pressure and number densities of an atmosphere as a function of altitude, then their interaction with respect to the solar radiation, and what which part of the solar radiation, which part of energy interacts with the species to create the thermal structure. So this is some kind of like, it's like an observation kind of thing. But if we want to actually model it and see it mathematically, so it is possible to do it. So generally, atmospheric processes are not a single process. All these processes, that means physical, dynamical, and chemical processes, occur simultaneously and they are coupled. That means if one process is dependent on the another process. So as shown in the first slide, so all these processes have to go hand in hand. And if you want to mathematically we need to solve certain equations with some boundary conditions and parameters. Now we will see if we want to solve this or model atmosphere, how can we do it? So the first thing what is important to understand for modeling the atmosphere is to understand what is the composition. Composition will tell us the species which are there, their masses, their cross sections, the energies required to by the radiation to undergo various processes, as I have mentioned earlier. So if we look at the Earth, our Earth has majority of nitrogen, then oxygen is the next dominant species, then you have argon and water. Whereas Venus is dominant CO2 atmosphere with a little bit of N2 and sulfur dioxide. The densities are relative densities are given here percentage. Whereas Mars is again dominated by CO2 atmosphere, a part of nitrogen, argon, and oxygen. So we should start with these species because these are the species which make up the atmosphere of each of these planets. Then how do we model? So if we have a chemical reaction, let us say A plus B gives rise to C plus D. So it is ultimately like a balance, chemical balance. That means what is the production and what is the loss. So rate of production of species C is given by D, that means rate of production is d by dt of C is nothing but K, which is the rate constant of A as well as B. So in general, for a chemical model, we generally use a continuity equation, which is nothing but it will tell the rate of change of an ith species with concentration N. So what is it? So d by dt, dni by dt means the rate of change of concentration of I species, where the concentration is N, can be simply written in terms of what is the production of the ith species and what is the loss of the ith species. So this equation of d by dt of ni equals to production minus loss is called as a continuity equation. The simple thing, if we want to know what is the net availability of that species during the process, so we solve the continuity equation by using the rate constant and the density of those species, so that we can get the the production or the concentration of that species at any given time, or rate of change of that concentration of that species. So how do we apply it? So we said it's a simple reaction, but a species can undergo several reactions, and all those reactions have to be taken into consideration. So let us take an example of ozone chemistry. So ozone chemistry is defined by all these Chapman reactions. Like for example, if we have an oxygen, so which can get photodissociated by radiation of less than 243 nanometers. So O2 plus a photon H nu can photodissociate it to O plus O. So let us label it as Ja. Then whatever this oxygen is there, and you already have O2. So O plus O2 in a three-body reaction, which is a third body M, can create ozone. So it can create O3, means this third body can act as a catalyst, and O plus O2 plus M can use this to O3 plus M. Let us consider this is as a Kb. Then, but what is this JKB? So that those are basically the reaction rates what are given by this. So then there is another process where O3 gets photodissociated within less than 310 nanometers to produce an O singlet D plus O2. Then again O3 can again get photodissociated for longer wavelength to give O plus O2. Then this O plus O3 has another reaction O2 plus O2. So this combined process can give rise to ozone. Either it can create ozone, that is a production, or it can destruct ozone, which is a loss. So depending on which is the dominant process, which is the dominant radiation which is there, so it will be get balanced and it will try to reach an equilibrium condition. So based on that, we will get the final species. So the above reactions basically describe the production and loss of ozone in Earth, Mars, and Venus, where Kb and Kd are the constants measured in the lab, whereas J and Jc are the constants which are determined by theory. So the continuity equations describing the rate of change of concentrations of O, O2, and O3 are shown in the next slide. So these are the continuity equations for each of these things. And the general continuity equation we have actually seen in a previous slide. So by applying these reactions and the continuity equations, we can actually find out the change of concentration of a species as a function of time. So this is only a single example for ozone. But an atmosphere doesn't contain only ozone. It contains several other species. It can contain carbon dioxide, it can contain carbon monoxide, it can contain nitrogen, it can contain water vapor. So it has several species, and all these species have to be solved in a set of such equations. It's a large set of equations which has to be solved in combination. And these are not only the neutral species, but also you can have ions. So if you consider all these things, that forms an atmospheric model. So a typical model for the atmosphere may have many species, but for example, there is one ion model developed at PRL, which will be described later. There are 35 ions which are considered. Now, we have considered physical process, radiation, and chemistry. But this is a static condition. That means whatever is happening, it is happening there. But that is not true in the case of atmosphere, because atmosphere has winds. It has that dynamics. So therefore, a transport, there would be a gradient. There could be a gradient with respect to what is at the positions. So if we consider the dynamics, then we consider a finite volume of air parcel, which contains the given atmospheric species or gases, which moves along with the velocity of the wind, whatever it is. So whatever continuity equation we have derived previously, which was we can call as a static one, can be derived to a dynamic one by using this, which is dou rho by dou t plus divergence of rho v, which is production minus loss. That means here not only chemistry is considered, but also your dynamics are whatever motion is also there, that is also considered. So continuity equation plus boundary conditions will now describe the spatial and temporal behavior of the chemical constituents. So any model, the previous kinds of model where there is no transport is simply a chemical model. Whereas if you include transport, then such models are called as chemistry transport models, CT. So which can have two basic things. One is the chemistry kinematics, where the system of coupled stiff ordinary differential equations are used, and basic equations of atmospheric dynamics can also be used, which is usually used in general circulation models, which will be discussed in brief, where we can have system of coupled nonlinear partial differential equations. So depending on what we are trying to address, means we are trying to look at kinetics, or you are trying to look at dynamics, so we use the respective kind of differential equations. So now let us look a little bit on the radiative process, what can happen. So one of the things is the photolysis rate. So what happens? So whenever a reaction happens, you may get a new species, but at the same time you can have some energy as well. So for example, O3 plus H nu can give rise to O plus O2. In general, if you are not considering O3 as a species, you can consider any species X is nothing but minus Jx. So this Jx is the photolysis rate constant, and it can be yielded by this. So this is basically a parameter which describes this particular thing. Like if you put ozone, it is for ozone. So it contains three main aspects. One is the quantum yield, absorption cross section, and actinic flux, which is omnidirectional. So basically, it is considered that if you have a molecule, then it will have some cross section. So in some cases, depending upon the photon, some photons can be fully absorbed, some photons may not be absorbed. So the probability for incoming photons would be sigma by. So using this, actually, we can calculate the photolysis rates, which is actually important for calculating the heating of the atmosphere. And why heating is needed? Heating is needed because heating is needed to be considered because heating will actually give additional energy to the atmospheric species, where it can give rise to reaction. So now, what we can have? So we can have a radiative transfer equation where it is defined by this. I'll not go to the details, but there are two things. So scattering and absorption both plays an important role. And then another thing is that you consider the spherical like a species. So the angle at which the what do you say your radiation comes is also important. So the angular part of source function is expressed in terms of spherical harmonics given by this equation. So the radiative transfer equation is solved numerically using discrete ordinate method. So having looked at the physical processes, chemical processes, dynamical processes, and then how to put in terms of a mathematical formulation or expression, and how to solve. Having known about this, so how do we apply for any physical problem? Like let us say that we want to understand about the global atmosphere by modeling. So what we do? So usually, if it is applied to a limited space, it is a static model, but it can be applied to the whole space, a whole globe. Let us say if you want to apply this atmospheric model to the whole globe, what needs to be done? So what is done is generally the whole globe is divided into a finite grid, considering finite volume. So that can be smaller, that can be larger. And this can be solved in all three cases, like it can be solved in 1 dimension, 2 dimensions, and 3 dimensions. This is some schematic for global atmospheric model, where based on latitude and longitude, you can have an horizontal grid, and you have a vertical grid based on the pressure. Means what is the altitude we are taking? 5 kilometers, 10 kilometers, 20 kilometers, like that. So if you use latitude, longitude, and altitude, that becomes a 3-dimensional model. So we need to solve the equations what we were discussing for each of these grids, and combinedly apply these to the subsequent grid. Then what are the processes that are involved? An example is given here. So these are the physical processes that one has to take into the model once if we are trying to model the dynamics of the atmosphere of the Earth. Like you say continent, you have ocean, then you have your hydrological cycle, then you have an atmosphere, then you have advection, then you have momentum transfer, there is a heat transfer, heat exchange, then you have your sea ice is there, there's an outgoing radiation, there would be an incoming radiation. So all these things have to be taken into consideration while solving such models. So such models which span to the entire globes is generally called as general circulation models, which are nothing but the system of differential equations which are based on physics, fluid motion, and chemistry. That means they involve the physical process, chemical process, dynamic process, along with radiation. So generally, if you want to apply it for a planet like Earth, the planet is divided into a 3-dimensional grid. As I have mentioned previously, So each grid can be small or large, so could be anywhere from 100 to 500 kilometer wide. Apply the basic equations with each of these grids, and then evaluate whatever results we get. You see what is the effect of those results on the neighboring grid. So this is how one can solve the general circulation model and try to understand about the atmospheric phenomena or dynamics which is happening. So in this way, you can, using general circulation model, you can have the temporal and spatial variability of the atmosphere for any planetary body. So what are the basic equations of general circulation model? So basically, these are the basic equations. So you have an equation for motion, you have a mass continuity equation, then you have a thermodynamic equation, then you have an ideal gas equation. So you have to solve all these equations combinedly to get for each grid. So how do we solve this? So it is not as simple as that. So you have to formulate the differential equations according to that, and then you can have dependency. You can have dependent equations. So these dependent equations can be time dependent as well as space dependent. Then you solve them combinedly. So this solution of these equations requires a very large thing. They are usually, you develop numerical methods to solve, develop such models, and using that, if you want to solve both quickly and high accuracy, so then we need facilities, very like a supercomputer, like high performance computing cluster. This is an example of Param Vikram 1000, which we have at PRL. So such kind of complex models have to be solved, need computing facilities like this to solve such things and to have a global picture. So now we have got some idea like how do we develop a model, how do we run a model. So, okay, once we develop a model, we try to understand the atmosphere, its physical state, its processes, its dynamics. What is that we are going to do? So that is useful to understand the scientific phenomena which is being there at that planetary body. So what generally I'll give a few examples. What are the kind of sciences one can study of planetary bodies using such models? One example is a study of the dust storm and their effect on Martian atmosphere. You can see this is a Martian dust storm. It is an onset and evolution. So blue means that there is no dust in the atmosphere. Red means that what do you say, high dust. And this is an actual 2001 global dust storm. And this is from thermal emission data, which is from Mars Global Surveyor. You can see that June 17, 2001, there is no dust storm. And then this is the slow onset of the dust storm. This is a global dust storm. So, and you can see that this is completely covered by dust storm by July. Then the dust storm is receding. So this is the onset evolution of a dust storm at Mars. So if you want to see this phenomena, this needs to be modeled. So what is the climatology? So using these models, so one can actually reconstruct how these dust storms are going to be. So because it is only a 1 year, if you want to see kind of dust storm, and these are the kind of parameters of the phenomena like a dust storm. So this is the climatology of dust on Mars, which was derived. So we have constructed 15 years of climatology of dust storms on Mars from MGS and Mars Odyssey. And the global dust storms have been found to occur almost every 3 years, where local storms occur every year. And you see that here the dust storm would be because it has a large optical depth. So now we'll go a little higher up from the atmosphere. So we look at the ionosphere. Basically, this is the general structure of ionosphere. So where this is a boundary of solar wind, basically called exosphere. You have solar photon. Apart from the radiation, what we have discussed in the previous slide. So solar energy also have photons, it has protons, it has energetic particles. So it has energetic particles, magnetic field, solar wind, protons. So lot of things are there, and they start interacting with the ionosphere. So maximum electron density is in the M2 layer, which is basically extreme ultraviolet solar photon. The M1 layer is by solar soft X-rays and associated electron imprinting. So you can have this kind of ionospheric structures, which you can see it on Mars, and you can have one meteoric ion layer. So then how do you reproduce such things? So that can be done by using models. So this is just a single observation. To understand the background phenomena for having this kind of observation, you need to do modeling. So this is one of example of complex ion dust aerosol model, which was developed at PRL. So this is just to give a feel of how a model is developed. So you can see that these are all the continuity equations which are solved, and you can see that this is the density of positive or negative ions. This is the electron density. This is the ion aerosols which is included, and this is the production rate, total production rate of ions, and this is the total production rate of ions or aerosols. So this is a one-dimensional continuity equation solved in steady state. So, and this is another example. This is 101 reactions taken in PRL model. So what you can see that this is in the beginning we have seen a very simple ozone, but here you can see lot of species, and all these species are dependent. And you have, as I have told you, if they have a photoionization, you have electrons, then you have other chemistries which are coming down, and then so these are all interrelated. So most of things wherever we have observations, these observations goes into this to predict whatever are the atmospheric dynamics or atmospheric chemistry which is happening. So such complex models are devised using the equations what I have mentioned, and these are done using such kind of supercomputers to derive the science. Now I will show you some of the results from PRL ion model. So you can see that ion density decreases due to ion attachment with dust. So basically what it tells is that your dust can play a major role in the production of ions, and D region may completely disappear during dust storm because of the presence of dust. So another thing is there, it is a steady state. So you can have that what happens if the dust is there in ion model. But what if the dust is in motion? So now you are bringing dynamics into picture. So it is possible to model the realistic scenario of the onset of the dust storm and movement of the dust storm and dust cycle. So how it is done? Generally, we will parameterize the dust injection from the surface, then allow it to be mixed, advected by atmospheric wind, and it will fall back to the surface. So this entire dynamic process have to be implemented in the model by equation. Okay. So this is taken care in a popular mass WRF model, which is a mesoscale general circulation model. And this model is being run at PRL. So based on that, we predict Martian dust devils via boundary layer turbulence. So we have observed 63 dust devils, and this is one phenomena. And the result is that, so these are two rover sites. One is a Curiosity and there is Perseverance. And these are the turbulence, which is used in dust transport models. So what is predicted is that there are more dust devils. As you can see, the turbulence is more at the Perseverance site than the Curiosity site. It means that there are more dust devils. There are more dust devils at the Perseverance site. So this is how, even if you don't have observation, using the models, you can actually predict the phenomena by taking the physical parameters into consideration which are observed on a planetary body. So I'll give you one more example of the photochemical modeling of ozone. Ozone and water vapor simulated by a photochemistry coupled by mass EGCM. These are some pictures of ozone column. What we have done is that we have considered that ozone is destroyed catalytically by odd hydrogen, and we see the production of ozone, and then we we derive the distribution of this ozone column as in the complete globe of Mars. And one more study is the convective vortices. So whenever you have a dust storm, so basically there would be a convective vortex. What happens is that when a surface heats, convection develops, air rushes in, a vortex forms, then the hot air rises. In this process, it lifts the dust as well. So these convective vortices are defined by pressure drops. So whenever there is a convective vortices, there can be a dust devil, and whenever there is a dust devil, there can be a pressure drop. That means if we can systematically monitor the pressure drops, so we can actually tell something about the onset and evolution of the dust. So these are certain such dust storms, so which are correlated with the convective vortices and also the what do you say pressure differences. So these are few examples, actual pictures taken by Mars. Then these are some dust devil detection using pressure measurements. Then this is how one can model the this is how one can model dust devils. This is how one can model dust devils. I'll not go to the details, but one can even model the dust devils using the numerical model. So this is the complex example of such a numerical model. Then we can do Earth atmosphere modeling as well. I'll not go through the details, but I'll give you that these are all the inputs because ozone is harmful UV radiation which gets absorbed in the stratosphere by this equation. So if you want to work the Earth model, so then you need to consider all these things. So this is one example of the output of Earth-based model. So with this, I come to the end of this talk. So where I think we have talked about what are the processes which form and make the atmosphere to evolve and how to mathematically define those processes and how to formulate those models and then how to solve those models. And after solving, what is the science we get? And I gave you one example of science for Mars as well as Earth. So this is an example, and thank you very much.